start. Okay. And we're on page 73, 73. And my voice is still not good. Do you guys know how long laryngitis lasts? Like, I'm trying to figure this out. I'm like, for God's sake, I feel it should be done by now. Anyway. There we go. So, chemists, lazy people that we are, always looking for a way to shorten how we write things down. So instead of writing our powers of 10 when dealing with hydrogen ion, or you'll notice that there's a notation here. It says H3O+. And you're going to learn about that more over the break, but I will just mention it right now, because actually the truth is, in water, why is it making noise? In water, if you have HCl, for example, it's been misbehaving lately. It started it yesterday. It doesn't want to write. It just wants to move things. So I may be cursing a little bit today. Okay. HCl plus water goes to, and what actually happens is that this hydrogen here goes and attaches onto the water. That's what really happens. So you actually end up with Cl minus and when we attach another hydrogen to the water, it becomes H3O+. And H3O+ is called the hydronium ion. And it is how hydrogen actually exists in water. How H+ actually exists in water. Okay, so not a big deal. Like I said, you're going to learn about that over spring break with Mr. Kolber. He's going to teach you about that. But yeah, so H+ doesn't actually just float around by itself. It attaches itself to water and becomes the hydronium ion. All right. Now, hopefully, you make so much noise. Try turning it down just a little bit. Thank you. Sounds good. So we have the log of 10 to the negative 3. What is the log of 10 to the negative 3? This is something you should be able to do in your head. Negative 3. Yep, it's going to move on me, isn't it? Negative 3. And similarly, if we have the log of 1 times 10 to the negative 5, it's 5.0. Why is it 5.0 and not just 5? Because of sig figs 1 after the decimal. Sig figs are after the decimal. Once we've taken a log, after a log, sig figs are only after the decimal. And that is because this 5 here is that 5, that negative 5 there is that negative 5 there. And powers of 10 do not count towards sig figs. What is the log of 10 to the 7? 7. And what is the log of 1 times 10 to the 4? 4.0. Now, throw 5 times 10 to the negative 5 and log it in your calculator. bumping against my face. That was the problem. Got it. Okay, what'd you get? Negative 4.3. Okay? And that's because the number 5 times 10 to the negative 5 can actually also be written as 10 to the negative 4.3. Those two things are equal. You don't really need to know that or understand it. You just need to be able to push the button on your calculator. So 10 to the negative 4.3. Now, chemists thought this was a pretty good idea to simplify things so we don't have to write times 10 to the whatever, but they're still stuck with a negative sign. And so because most concentrations are less than 1, they will have a negative power of 10. So in order to eliminate that negative power of 10, they made it positive. Okay? And pH, remind me, what is the formula for pH? Tell your partner. Remind your partner, what is the formula for pH? What is it? Everybody.
Minus log of pH.
Negative?
No, 10 to the power of negative 8.
Negative log of concentration of hydrogen ion. Okay? Or, because we've just learned about that hydronium thing, we could write it as the negative log of, what was the hydronium ion again? H3O plus. Okay, either way is good.
Will it make a difference?
No, it won't make a difference. This is like the shortcut. And then this one is reality. Yeah? So if you're going to be doing a pH calculation, you should show all your work. And that includes the formula. So if we're calculating pH, we say pH is equal to the negative log of hydrogen, and that is equal to the negative log. In this case, actually I should have written hydronium because that's what we are given, H3O plus. So that's the negative log of 3.0 times 10 to the negative 3. And we don't have to put a unit in there because pH does not have a unit. And could you please plug that into your calculator and tell me what you get? You get 2.52287, and then some other stuff. What should that round to? 2.52. Because we have 2 sig figs here, and we have 2 sig figs here. Only after the decimal because we've taken a log. Okay. And it says here again, only the digits after the decimal point are significant in a logarithmic number. Okay. So you try these examples, see what you get. Show all your work as well as the answer. So if you want to check the first two, one thing you might notice about them is that they both have the same coefficient in front of the power of 10. They are both 5.4 times 10 to the something. And you can see that they end up with the same number after the decimal. Yeah? And that shows that the coefficient, the part with the sig figs, is really taking place after the decimal. Okay? Okay, and just watch that you had the 15.0 has 3 sig figs, and so for C, you should have had 3 numbers after the decimal to have 3 sig figs. And these two are in here to prove that you can have fairly low pHs and fairly high pHs. You'll notice this one went above, what's the word I'm looking for? It went above 15, 14, went above 14. Okay, we are now going to look into. Oh, yes. I'm sorry, I should have had a negative number there. And that shows that it can be a negative number, yes. Thank you very much for catching that. The prefix auto means self. Ionization means turning into ions. So what's going to happen is water is by itself going to turn into ions. And we're going to start with the shorthand method. I should stop using that word because none of you know what shorthand is. Does anyone know what shorthand is? No. It used to be back in the day when they had when there was no dictation, speech to text or anything like that. Very often people who were higher up in a company would have a secretary, and they would just dictate their letter to the secretary. And in order for them to be able to keep up with the pace of speech, there were little shorthand things, and the shorthand, they would stand for syllables and things like that. It looked like, let's just go look and see some shorthand.
It's just what doctors learn.
No, but it certainly looks like it. So there's like little squiggles and things so that instead of having to write out full words, so right would go it become that thing there, and apple would become that, and never would become that. I'm not sure if it's that much faster, but anyway, that's how it worked. And that was somebody's own personal shorthand. That's not a real official shorthand. And then we have things like bet, bat, bit, ball, bait, beat, boy, bus, bug, boot, Okay, there's all sorts of little things that just mean whatever. And people would learn it. They would literally go to school and learn it so that they could take dictation and be paid huge amounts of money less than the person that they were taking the dictation for. And then they would type it up. And then they would send the letter. Anyway, shorthand means making it shorter. You can call it a shortcut method. That might make more sense. And basically all it is you take water, H2O, which is of course what state? Liquid. And it dissociates into H plus, which is aqueous, and OH minus, which is aqueous. And that is the reaction that you will find on your data table, okay, at the very bottom of the white section. So if we go and we look on page 6 of the pink booklet, we have water goes to H plus plus OH minus, and that is actually water acting as an acid because it's giving off hydrogen ions. And what is the KEQ for that?
It's like the special number.
It's that special number. What was that special number? Feel free to look it up if you don't know it.
Like 10 to the power of negative 14.
10 to the power of negative 14. 1.0 times 10 to the negative 14. Okay. Now, in reality, is that what happens? No. Because remember, this hydrogen ion is the shortcut. In reality, what you have is you have one water, H2O, gets together with another water, H2O. Both of those are liquids. And one of the hydrogens goes from here to, actually I'm going to have it go from here to here because that's usually how we write it. One of the H plus ions gets attached to that first water, and then it becomes H3O, and because that hydrogen also had a plus charge, this also needs to have a plus charge. What is left when that second water gives away an H plus? OH. OH minus. Aqueous. Okay, so those are both different ways to write the auto-ionization of water. In reality, water is acting as a, and this is a word you're going to learn next week, it is acting as a Bronsted-Lowry acid and is a Bronsted-Lowry base. Now, what the heck is a Bronsted-Lowry acid and a Bronsted-Lowry base? Well, a Bronsted-Lowry acid is a substance that donates H plus ions to another species. So the Bronsted-Lowry acid donates H plus ions to another species. So that's a definition of an acid, a particular type of acid. You will also learn over spring break about Arrhenius acids. And Arrhenius acids are like, they just throw hydrogen out into the water. Okay, so you'll learn about those. We also have the Bronsted-Lowry base. And the Bronsted-Lowry base, that's going to be, actually, sorry, you got that wrong. Our Bronsted-Lowry acid is the one that gives away the proton. And the Bronsted-Lowry base is the one that, what does it do with the proton? It doesn't give it away, it receives it. So it is we actually say a proton acceptor. Okay, a Bronsted-Lowry base accepts an H plus ion from another species. What do we call animals who can live on both land and in the water? What do we call those ones? We call them amphibians. Yes? Amphibians, because they can live both places. Okay? Amphi means both. Now, the other thing I'd like you to think about is I'd like you to think about an H atom. What's in the middle of an H atom? This is easy. This is grade 9 stuff. What's in the middle of an H atom? A nucleus. What particles are in the nucleus of an H atom?
Neutrons and protons.
Neutrons and protons. How many protons and neutrons are in the nucleus of a hydrogen atom? Please go look on your periodic table if you don't know.
One proton, one proton and I forgot the 0 neutrons.
One proton. It has a mass of 1. So how many neutrons does it have?
How do you calculate neutrons?
How do you calculate neutrons? So if you have hydrogen, and you got the atomic number 1, what does that tell you? That tells you the number of protons.
big proton times.
And then we have the atomic mass, which normally we wouldn't use this way, but let's just say we're going to say that's the average, it is the average mass. On average, how many neutrons does it have? What are the particles in an atom that have mass, have significant mass? Neutrons and protons. Only protons and neutrons have significant mass. So, what is the mass of one proton? Mass of one proton or one neutron is 1. Anyone remember the unit for that? A M U, atomic mass units. Okay, so if this is our atomic mass, this is our average atomic mass, then how many neutrons are in this atom? You have one proton, right? One proton. And this atom has a mass of 1. So how many neutrons do we have? 0. Because if we had 1 neutron, they also weigh 1. It would have a mass of, if you have something that weighs 1, and you have another something that weighs 1, it would have a mass of 2. But we only have a mass of 1. So the hydrogen atom has 1 proton, 0 neutrons. How many electrons does it have? A hydrogen atom. Just 1, because it's neutral, yes? So we have 1 electron. So if we were to draw that, it would look like this. Here's our proton in the center. And our electron is going around the outside. That's a hydrogen atom. How would we draw a hydrogen ion, an H+ ion? What would happen to that? How many protons, how many neutrons, how many electrons? Does the number of protons change when we go from being H to being H+? Does the number of neutrons change? No. Sorry, does the number of protons change? No, because otherwise it would not be H anymore. 1 proton. Number of neutrons stay the same. 0 neutrons. How many electrons? 1 or 2 or 1 electron? Hold on. Down here we had a positive and we had a negative, and +1 and -1 make 0. Right? +1 and -1 make 0. Do we still have 0? Is that charge of that hydrogen ion 0? No, it is +1. How many electrons do we have in that ion? Yes, yes. It is 0. There are 0 electrons, right? Because that gives us a 1+ charge. So what would that look like? Here was our hydrogen atom. What would our hydrogen ion look like? It's just a single proton. So a hydrogen ion is just a proton. Okay, H plus ion is just a proton. So we will actually call H plus a proton. Okay? In the acid unit, so when we talk about a Bronsted-Lowry base, or sorry, a Bronsted-Lowry acid, when we say it donates H, can tell where my mind is. I'm like, breakfast, second breakfast. Ooh, yeah. When it donates H plus ions, it donates protons. Okay? Because an H plus ion is a proton. A Bronsted-Lowry base accepts H plus ions, but instead of saying H plus, what could we say? We could, but not in this case, a proton. So Bronsted-Lowry acids are proton donors. Bronsted-Lowry bases are proton acceptors. Okay? You're going to go all through this over spring break, so don't worry if this is kind of like shh. Okay? Now, all of that comes back to say that water is both donating protons and accepting protons. It is acting both as an acid and as a base. So if it does both things with protons, we can say that water is amphiprotic. It does both things with protons. And by doing both things, I mean donates and accepts. And now, what we're going to do is you are going to take both equations for the autoionization of water. Remember, those were up here. Okay, those are our autoionization of water. And you are going to write the KEQ expression for each of those reactions. Okay, so please do that. Please write the KEQ expression for reaction number 1 and reaction number 2, those two autoionizations of water. So hopefully you got two KEQs that look like that. You've got hydrogen concentration times hydroxide for the first one, and hydronium times hydroxide for the second one. These are the same. Okay, remember this one is the shortcut. This one is reality. And both of those have a special name. What is that special name? It's the KEQ for water. KW. Okay? So this is KW. And now we are going to use hydrogen or hydronium to find the concentration of hydroxide. So we are given concentration of hydronium is equal to 3.0 times 10 to the minus 3. What is the formula for KW? You guys are killing me. What is the formula for KW? H times OH. Okay? What is the other formula for KW? H3OOH. Thank you, Owen. Appreciate it. Now, all you need to do is rearrange that formula to solve for OH. What is OH equal if you solve for OH? KW. And in this case, we're going to use H3O plus because we were given H3O plus. What is the value for KW? 1.0 times 10 to the negative 14 divided by H3O plus is 3.0 times 10 to the negative 3. So that's going to give us 3.33 times 10 to the negative 12. How many sig figs should we have? 2. 3.3 times 10 to the negative 12. Am I missing anything in my answer? Units. It's concentration, so the unit is capital M molarity. Is that relatively straightforward? Okay, so anytime I give you hydrogen, you can find hydroxide concentration. Anytime I give you hydroxide, you can find hydrogen because you have that relationship between them, and that is KW. pOH. pH, what's the formula for pH? Negative log H plus. What is the formula for pOH? Negative log OH. Showing all of your work, please find the pH and pOH of these two solutions. Or no, this is just one solution. They are, because this is the one that we just did in example 2 where we said our hydronium concentration was 3 times 10 to the minus 3, and we said, what's the hydroxide? The hydroxide is 3.3 times 10 to the minus 12.
We need to solve for pOH.
Hmm?
We need to solve for pOH.
We need to solve for pH and pOH.
We already solved for one of them.
Have we?
Oh, wait, no, we have.
Once you're done, check your answers with mine and see if you're happy with my answers or if you think I could do something better. I could do something better? Oh my gosh. What could I do better? Sig figs. So I got 2 sig figs here. And that means that's going to round to 2.5. No. What should it be? 2.52, because our sig figs are there. Okay, very good. And our last one, same thing. It's going to have 2 sig figs, so it's going to become 11.48. Excellent. Okay. Why did I give you all the work here? Oh, because I wanted to show you what you should show for your work. This is the work you should show. To find concentration of OH and pOH. So you would say, okay, I have hydrogen and I want to find hydroxide. In order to find that, I need to use kW. So write out the kW and then rearrange the kW so that you've found hydroxide. And then plug in your kW value, your hydrogen value, and you get your hydroxide ion concentration. And what did I miss there? That should have been molar. And if I was asked to find hydroxide, what should I actually do with that number? That number should become 0.00 19. Now, if I go on to the next step, do I want to put 0.0019 in here?
No.
Is that okay? No. Keep your unrounded value so you don't end up with a rounding error later. Okay, what would we get if we did 0.0019? Let's try 0.0019 log. That would give us 2.721. The negative log of 0.0019 is 2.721, which would round to 2.72, and that is a rounding error. Okay, so don't round off until the very, very end. All right. You guys get to do the next one.
For example, 5, how do we know pKw is what pKw is?
pW is always 1.0 times 10 to the negative 14 at 25 degrees Celsius. Of course, because it is a K value, what would happen if we changed the temperature? It would go up or down, and we'll deal with that later. You can assume that unless we say otherwise, we are at 25 degrees Celsius. Okay? So all of this stuff that we're doing today is pretty easy. It's pretty straightforward. It can be pretty tedious, but you want to get good enough with it that you don't have to think about it. Because not only are you going to use it in this unit, but you're also going to use it in Unit 5. And you're going to have to remember it in Unit 5 because we're going to do Unit 4, which we're doing right now. We're going to go away and you do Unit 3, and then we're going to come back and do Unit 5. So we're going to do acids and bases, then solubility, and then come back to acids and bases later.
Not like 1 decimal off.
What did you get?
I got 7.72.
Did you round off?
No.
No?
It has to be 7.7.
Let me see. 1 times 10 to the negative 14 divided by 5.4 times 10 to the negative 7 equals, I get 1.85185. And when I take the log of that, 1.85185, I don't do anything. Like I've got that number in my calculator, and now I press log, and I get 7.732. So yeah, 7.73. Yeah? Are you getting a different number still?
So what I do when I calculate for OH,
Yep.
it should have given me like exactly this.
Okay. But your calculator knows more digits than that. Do you know how to put that in scientific notation on your calculator? Do that.
Oh.
Yeah? So the problem James was running into is his calculator was giving him 0.1, 2, 3, 4, 5, 6, 7, 8. Oh, whoops. 19. Yeah, and it wasn't showing anything after that because the calculator ran out of digits. But that's not what the real number is. You should be able to, your calculator shouldn't round that off. If you just use that number and take the log of it, it should actually give you 0.000185,185. But if it's a crappy calculator, put it in scientific notation first so that it has all those other digits in its brain. Is that working now?
No, I just straight up put a log in. I just put the whole thing in.
Yeah, that's what you do. Yeah, log the whole thing. Yep. Okay. Yes. 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 Huh? Oh, because this is molarity, not pOH. We've not taken a log. No log yet. No log yet. So these are 2 sig figs. Now log 2 sig figs. Yeah? Now, I don't know, do you feel like you need to do any more examples on this, or are we good to move on? Because they're just exactly the same. Anyone want to do more just like that? Yeah? Oh, okay, well, let's do one more. Let's do that really big hydrogen value there. So you are finding hydroxide and pOH. Right? No, it's not. Like, that's just not a good number there, sorry. Yeah, times 10 to the negative 16, times 10 to the negative 16. There we go. Times 10 to the negative 16. I'm like, that's an impossible number. Did I do it right? sig figs. Whoops, what happened there? It went away. Is good? Do we want to do example 7? No, we're good? All right, excellent. All right. So we know that if you take the negative log of something, you get p something, right? This little bit here. Negative log gives you the p. Negative log of hydroxide gives you pOH. Negative log of Kw gives you pKw, which is the one that people always forget. Now, we're going to play with this a little bit. Unless you don't want to see this, you don't need to know how we derive this, but it's probably good for your brain. Yes? So we're gonna play around with it a little bit. So if we have a hydronium concentration of 1 times 10 to the negative 5, hydroxide is going to be, so we have our hydronium down here, we have our Kw, which is 1 times 10 to the negative 14, and we end up getting our hydroxide, which is 1 times 10 to the negative 9. Now, without hauling out your calculator and without looking at the answer, what is the pH? Could you just do that in your head at this point? If we have 1 times 10 to the negative 5 hydronium, pH would be 5. And if it's 1.0 times 10 to the negative 5, it would be 5.0. 5.0. Uh-oh. 5.00. 2 sig figs, 2 sig figs. So if your coefficient is 1, you don't need to haul out your calculator to do it. You can just be like, oh, there's my power of 10, right? And make it, and take the negative of it, okay? Now, our hydroxide ion concentration, what would our pOH be? If our hydroxide concentration is 1.0 times 10 to the negative 9. pOH would be 9.00. 2 sig figs. 2 sig figs. Okay, now, if you were like, no, I would prefer to just, do the math and show the work and everything, that's fine. You can do that. You can plug that into your calculator and you'll get the same answers. So when we add these two, our pH plus our pOH, what do we get when we add those two? We get 14. There we go. So pH plus pOH equals 14. You are not responsible for being able to do this derivation. But if you have done your logs in math, in theory, you should be able to follow along with this. We have Kw. Kw is equal to hydrogen times hydroxide. We're going to take the negative log of the left side, and we're going to take the negative log of the right side. If we do it to both sides, they stay equal. Yes? Okay. Why negative log? So that we can get a pH, okay? Now, if you remember your log rules from math class, log of A times B is equal to the log of A plus log of B.
Learned that like yesterday.
Okay, well look, and here you are using it in context. Log of A times B is log of A plus log of B. And look what we have here. We have A times B. Yeah? With a negative log of A times B, H times OH. So, from a mathematical standpoint, we can say we have the negative log of H plus the negative log of OH. Yeah? That we're just throwing the negatives in there because chemists are weird and they needed to throw that negative in there. Now, you know that the negative log of Kw is called, negative log of Kw is pKw. Negative log of hydrogen is, work with me here, people. Negative log of hydrogen is pH, and negative log of hydroxide is pOH. Excellent. So we've ended up with pKw equals pH times pOH. Well, what is pKw? Well, it is the negative log of Kw, and Kw is 1 times 10 to the negative 14. pKw is negative log of 1 times 10 to the negative 14. And so we get 14.00. Okay? So 14.00 pKw is equal to pH plus pOH. So at any temperature, excuse me, at 25 degrees Celsius, it's equal to 14. At any temperature, pKw is equal to pH plus pOH, but the pKw will vary at different temperatures. So this is not 14, if not at 25 degrees Celsius. Which has some weird little things like, you know, if your temperature is high enough, pH 6 is neutral. And that's fun. We'll learn about that after the break. Okay, so Hebden on page 138 has a following handy little conversion chart. Okay, and if you're into memorizing all of these things, you might commit this little table to memory. We're going to add on to it though. So if you want to go back and forth between hydronium and hydroxide, you're going to use Kw. If you want to go back and forth between pH and pOH, okay, then you're going to use, so if we have pH and pOH, oh, let's make that one blue. Pink. No, I've already used blue. Let's use green. Okay, good. There we go. Okay, so that's 14.00. So that gets us back and forth from pH to pOH and from hydrogen to hydroxide. And Kw, of course, is 1.0 times 10 to the negative 14. Now, we know for sure that pH, going from top to bottom, pH is negative log of hydrogen. And we know that pOH is the negative log of hydroxide. And the only thing that we are not able to do with this chart as it is to go up. Do you remember how to find concentration of hydronium or hydrogen given the pH? You can't. You could go, you know what you could do? You could go like all the way around the loop, but that's an effort. And if my pH is 5, what's my hydrogen ion concentration? 10 to the -5. Yeah? So hydronium or hydrogen is equal to 10 to the negative pH. And on the other side, we have hydroxide. And if we want to go from pOH to hydroxide, hydroxide is equal to, how do we find that from pOH? 10 to the negative pOH. This chart is worth devoting to memory, okay? Okay. Now, this 10 to the negative pH business is also known as, whoa, what happened there? Antilog. And I'm introducing this to you because you should be aware of the terminology. Okay, so basically, if we find the pH, we log the H. Whoops, sorry. We log the H, and then, number 2, we change the sign. So to go backwards, we need to change the sign, negative pH, and then we anti-log it, which is 10 to the exit. So you could, if you wanted to, write hydrogen ion is equal to the antilog of the negative pH. But I find it's usually more convenient, and because it looks like this on your calculator, to write it as hydrogen is equal to 10 to the negative pH. But it means the same thing, just so you're familiar with the terminology. So if you see it, you don't get confused by it. Okay? So if the pH is 4, hydrogen is 10 to the negative pH, which is negative 4.0, which is, now, this is very simple, but how many sig figs in the pH? Remember, pH is a log number. Yeah? How many sig figs in 4.0? 1 sig fig. Right? because pH has had a log taken. Anytime you have a p-value, p-values, they're decimals, their sig figs are only after the decimal. So p-values, sig figs are only after the decimal because they have had a log taken. So we have 10 to the negative 4.0, we still have 1 sig fig. And so when we answer that, it's going to become 1 times 10 to the negative 4, 1 sig fig. What if we have pH is equal to 1.00? How many sig figs in that number? 2 sig figs. And so hydrogen is 10 to the negative pH, which is 10 to the negative 1.00, which is 10 to the positive 1. Which is just equal to 10. And so how many sig figs should we have there? 2 sig figs. How do we give 10 2 sig figs? No, because this is molarity, not a log, not a p. 10 has 1 sig fig. 10 with a dot has 2 sig figs. Or you could write it as 1.0 times 10 to the 1. 2 sig figs. Alrighty. And one last example, and then we're done. If our pH is 7.320, how many sig figs in a p-value? 3 sig figs. So hydrogen is the anti-log of negative pH. You could write it that, or you could write it as 10 to the negative 7.320, which is equal to 7.320 negative anti-log, and we get 4.7863 times 10 to the negative 8. What should we round that to? 4 point. And remember, this is now a concentration, so that's molarity, not a P. So sig figs are normal. So to have 3 sig figs, 4.79, 3 sig figs times 10 to the negative 8 molar. Okay? We will review all of this when we get back from spring break. Does everybody have a copy of the spring break homework? And you remember, as long as you have completed it, you get 10 out of 10. But if there's any parts missing, then you don't get 10 out of 10. Yeah? So make sure you do it. It's like a little present, right? Good stuff.